Okay, what we're going to talk about in section 13.1 is how to determine when a function is increasing and decreasing. Hopefully you graphed the function that I gave you and found the information that I asked you to find before you're watching this PowerPoint. If not, please do stop and do the preparatory lesson for this lecture. So, increasing. The idea of increasing is that something is getting larger and larger and larger, and if it's decreasing, it gets smaller and smaller and smaller. And that idea is pretty intuitive to most of us. Okay, in chapter 13, we're going to actually continue with the things that we learned in chapter 12 about rates of change and derivative. But at this point, we're actually going to be using those to learn more about certain aspects of functions, and especially in an application setting. So section 13.1 is talking about when a function is either increasing or when it is decreasing. And good logical common sense idea of increasing is when something gets bigger, and it decreases when it gets smaller. And we're talking about the value of the function increasing or decreasing as the x values change. So to begin with a kind of an intuitive idea of how this works, all three of these examples are examples of increasing functions. And when we talk about increasing functions, it's important to notice that we're talking about what happens to the function which is f of x, as x gets larger. In other words, as x increases. So we're always going to be talking about where x is increasing, not about where it's decreasing. So notice here on the first one, as x gets larger, f of x also gets larger. And in example B, as x gets larger, f of x gets larger. And even in example C, as x gets larger, in other words, as we're reading from left to right, the value of f of x also gets larger. In contrast, in example D, what we see happening is that if we start from left and move toward the right, that the values of f of x decrease as x gets larger. And again, in example E, in the linear function, as you move from left to right, as x increases, f of x decreases. So you're focusing on the values of the function, not the values of x. X is always going to be taken to be getting larger and larger. And so this function also, as x increases, this function constantly decreases. The pictures, but when we get to examples D, E, and F, we're looking at decreasing functions. These functions are going downhill. They're losing value as x increases. And again, we're looking to see where x is getting larger, which means we're reading the x-axis from left to right. And when we read that graph with x going from left to right, starting here at smaller values of x and moving along the x-axis, you see the values of the function get smaller and smaller. And the same thing happens with the linear function. As x gets larger, f of x gets smaller. And again, with this function, as x gets larger, f of x gets smaller and smaller. So this is the mathematical definition of what it means to be increasing and decreasing. If x is a function defined on some interval, and for any two numbers where x sub 1 is smaller than x sub 2, And notice that's what it says on both of these. As you move from f of x sub 1 to f of x sub 2, or excuse me, as you move from f of x sub 1 to f of x sub 2, the function is increasing if the first of the two x values produces a smaller value than what the second or the larger x value does. So we said that that is an increasing function. And the function is said to be decreasing as long as x sub 1 is smaller than x sub 2 if the value of the function at x sub 1 is higher than the value at f of x sub 2. But truthfully, the definition is than the words do, as is often the truth in math. And so this is the formal mathematical definition of what it means for a function to be increasing and decreasing. And basically they're just saying for any two numbers where x sub 1 is less than x sub 2, so it's smaller than x sub 2, then the value of the function at x sub 1 is also going to be less than the value of the function at x sub 2. That means the function is increasing. And f is actually decreasing when the value of the function at the first x value is the larger of the two. So this means that the function is going uphill from x sub 1 to x sub 2, and this way the function is going downhill from x sub 1 to x sub 2. So let's talk here about where is f of x increasing, where is it decreasing, and where is it constant. And first of all, we notice that f of x has some changes in behavior at -4, at 0, at +4, and at 6. So paying attention to those particular x. And so to kind of solidify that, we're going to talk about where is this function increasing, where is it decreasing, and then sometimes functions are neither increasing nor decreasing. They're simply constant. So we'll talk about when we know that happens. So looking at this function, we notice there's some important numbers where this function changes behavior. This is one of the points where it goes from being going in one direction to changing to another direction. Also at this value, and then at this point also, the values -4, 0, and 6, the value of f of x actually changes behavior over that interval. And the other important number is at 4. So we've got 4 numbers here on this function that indicate changes in the behavior of the function. So we're going to examine the functions. We see that this function is in fact increasing as x goes from -infinity and it stops increasing when it gets to -4. And we see that it is also increasing when x goes from +4, but it stops increasing once again at 6. And first of all, we see that f of x is increasing on the interval from -infinity to 4 because the function is actually moving uphill. And it's also increasing on the interval from 4 to 6 because the function is moving uphill. Similarly, we're going to see that f of x is decreasing as x goes from -4 to 0. And we see that it is also decreasing as x goes from +6, and remember this is also approaching infinity. on the x scale. We also notice that the function is decreasing on the interval from -4 to 0 because the direction the function is traveling is downhill. And it is also decreasing on the interval from 6 to positive infinity because the function's behavior is that it is traveling downhill. And even though we have not defined not particularly defined this term, we also see that f of x is neither increasing nor decreasing on the interval that goes from 0 to 4. It remains constant. We will say that f of x is constant on the interval from 0 to 4. And then lastly, we notice that on the interval from 0 to 4, the function isn't increasing or decreasing, and we say that it is constant on that interval, which means it's not increasing, it's not decreasing. Another way that you can think of increasing and decreasing functions is you could think about roller coasters. If you start out on the roller coaster, you usually start out, of course, on the ground. And usually the roller coaster starts off going uphill. But at some point, it reaches the top of that hill, and maybe just to kind of get you used to the idea, you might go down a little decline, which means your function might seem constant for just an instant at about 2 minutes, or maybe this is 2 seconds. But then from that point on, up until about 4 seconds, then the roller coaster is again going uphill. And then at about the 4-second mark, you top the hill, and there's where the thrill ride begins. So again, increasing uphill, both of these intervals, decreasing downhill, but your rate of change is 0 in between positive and negative slopes, as it is here, and also it would be 0 for just an instant at the very top of that hill before you take the plunge. You could think of it as a roller coaster, where you get on the roller coaster here, and for about the first interval of time, let's say for about a second, you climb, but at x equals 1, you go downhill a little bit, and just for an instant at time, let's say 2 seconds, you've actually kind of hit the valley. And then from 2 seconds until you get to 4 seconds, you're actually going uphill again. And then at 4 seconds, just for an instant, you're sitting on top of that hill before it's time for the thrill and you're going downhill very, very fast. The reason we use calculus to talk about this is because this is actually the mathematical definition for when the function is increasing and decreasing. And the first thing I would remind you is that we're talking about the derivative of the function. And when the derivative of the function is positive, that means its rate of change is positive, and that means that it is increasing on that interval because it's going uphill. If the derivative is negative for all the x's in that interval, then we would say that f of x is decreasing on that interval because it's going downhill. And then we would also say that if the value of the derivative is 0 in an interval, then f of x is actually constant on that interval, which means that its slope is 0, or it basically is horizontal at that point. So it's not increasing and it's not decreasing. So we're going to talk about what's called the derivative test. To find out where functions are increasing and decreasing. And so first of all, we're going to talk about how to find out when a function is increasing. And notice that we're talking here, in this case, about its derivative, because the derivative is the rate of change. You need to remember that. And rate of change is another word for slope. And we know that slope can be either undefined, which means it's vertical and there is no derivative, or slope can be negative, it can be 0, or it can be positive. And so we're going to talk about those different scenarios. So if the derivative is positive, then we say that f of x is increasing. And if f of x is negative, then we say that the function is decreasing on that interval. And then lastly, if it turns out that the derivative is actually 0 at some point or points, then we know that the function is constant on that interval. And in other words, it's not changing, it's not increasing, it's not decreasing. And that's going to turn out to be a really important idea for us as we look for where functions either reach a maximum or a minimum, because those concepts can be very important. One of the important concepts that we're going to learn about in this section is something called a critical number. The critical number for a function is the values, and we're going to call those C, in the domain of the function, because remember, some functions have domain restrictions. But we're going to say the critical numbers are where either f of c is equal to 0 or f of c does not exist. Both of those are called a critical number. And a critical point is the point whose x-coordinate is the critical number c. And the y-coordinate is then, of course, f of c. So the first thing in using the derivative test is we have to find something called the critical number and the critical points. And a critical number are where the value of the function is equal to 0, or when the value of the derivative is equal to 0, not the function, or when the value of the function, the derivative, does not even exist. And so the critical points are whatever x values, which we call c for critical points, give us either the derivative being 0 or the derivative not existing. And what we're going to have here then is a test. We're going to call it a derivative test for when the function is increasing or decreasing. And this is how we apply that test. First, we locate the critical numbers for the function on a number line. Critical numbers being where the value of the derivative is 0 or the value of the function, and therefore its derivative also, are undefined. So we're going to locate those critical numbers, and that's going to give us several open intervals. And then we're going to choose a value of x in each of those intervals and use those values to determine whether the value of the derivative, not the function, the derivative, is positive or if it's negative on that interval. And if f of x is greater than 0, then we know the function is increasing. And if f prime of x is less than 0 or negative, then we know the function is decreasing. So this is the actual derivative test that we're going to use. Our first step is going to be take the derivative, and then using that derivative, locate the critical numbers. Then you're going to choose an x value in each of the intervals from step 1 and decide whether or not the derivative is positive or it's negative. And when the derivative is positive, that tells you that the function's rate of change is positive, therefore the function is increasing. And when the derivative is negative, we know the rate of change is negative, which means your function is decreasing on that interval. So here we're going to do our first example. So we're going to look here at an example. And our first example says, determine the intervals in which the following function is increasing and decreasing, and locate all points where the tangent line is horizontal. Then we're going to graph the function. Well, the first thing we need to do is we need to find the value of the derivative of this function. So in order to find the value of the derivative of the function, then we use the power rule. And this is the problem that I gave you to do before you actually started viewing this. Hopefully you've done that. And so the first step is going to be to find the derivative. So the derivative of f of x is 3 times x to the 3 minus 1 is 2, plus 2 times 3 is 6, x to the 2 minus 1 is 1, minus 1 times 9 is negative 9, x to the 0, and the derivative of positive 4 is 0. So here's our derivative. And the second step is finding the critical values. And so to find the critical values, we're going to take that derivative and we're going to set it equal to 0. Now, there's two ways to solve for x here. You can use quadratic formula. But this one happens to be one of the ones that lazy people, even lazy people like me, notice has the greatest common factor. So if I factor out the 3, it turns out that this one can actually be solved by factoring. And so I am going to solve it by factoring. And if you remember solution by factoring, this is equal to 0 if x minus 1 is equal to 0, which would happen if x was 1. And if x plus 3 is equal to 0, which happens when x is equal to negative 3. And so these are our two critical values. We don't have to worry about this function being undefined because its domain is all real numbers, because it's a polynomial function. So here now we have our critical values. Negative 3 and 1. And they divide our x values on the number line into 3 intervals. The first interval goes from negative infinity to our critical value, negative 3. Our second interval goes from negative 3 to 1. And our third interval goes from 1 to positive infinity. And then the next step is to take the value of the derivative at one number in each of those intervals. And so the smallest or the easiest one to plug in the interval from negative infinity to negative 3 might be negative 4. That's going to be our test point. And what we find is that f of negative 4 is positive. Doesn't matter really what the value is. You're interested in whether it's positive or negative or 0. And this one happens to be positive. You can check that one out. The easiest one to check out is the test point from negative 3 to 1 is to choose 0, because 0 means 3 times 0 squared is still 0, plus 6 times 0 is still 0, minus 9. So f of 0 turned out to be negative 9, but the key was that it was negative. And then we're also going to test 2, 3 times 2 squared minus 6, or excuse me, plus 6 times 2 minus 9 is in fact positive. And so what that tells us is that on the interval from negative infinity to 3, the value of the function is positive. And on the interval from negative 3 to 1, the value of the function was negative, and therefore, or the value of the derivative was negative, and therefore the function is decreasing. It has a negative slope. And then again on the last interval, we see that going from 1 to positive infinity, that the value of the derivative was positive, which tells us the function is increasing. And this is the test that I will expect you to use for whatever function that I give you to tell me whether it's increasing or decreasing. Now you can verify your answers using the graphing calculator because you can actually graph the function. But the part that makes it easier for you to graph the function is knowing what these critical numbers are and having an idea of whether or not the function is increasing and decreasing on those intervals, because that actually helps you choose your domain. So you do need to know how to find those critical values. And so we see here, this is the function that I gave you to graph and answer questions about before class. And notice that it is exactly as we said it was. The function is increasing on the interval from negative infinity until we got to the critical value, which was negative 3. Then it became decreasing on the interval from negative 3 to 1, our second critical value. And then it returned to increasing again from 1 to infinity. So here's another example that we're going to do. And what we want to do here is we want to find the critical numbers and decide where f is increasing and decreasing given this function, f of x is equal to x minus 1 raised to the 2/3 power. So the first thing we need to do, the first step in our increasing and decreasing functions test, is to find the value of the derivative. There is no value of x that would cause the denominator to be so large that 2 would ever turn into 0. Now, if you need to prove that to yourself, it's not hard to prove, because all you have to do is take two over 3 times the cube root of x minus 1, set it equal to 0 over 1, and cross multiply. And 2 times 1 is 2, but 3 times the cube root of x minus 1 times 0 turns out to be 0. And of course we know that that is not possible. So there is no x value that causes the derivative to be equal to 0. However, remember, you also need to find out where f prime of x is undefined. And for that, we have to consider, when would 3 times the cube root of x minus 1 be equal to 0, because division by 0 is undefined. And that would be when the cube root of x minus 1 is equal to 0, because obviously 3 is not 0. And if I cube both sides of this, that means that it's going to be where x minus 1 is equal to 0, which happens when x equals 1. So this is your critical value. So keep in mind, very important, you also have to remember the conditions under which a function is undefined. Sometimes it doesn't have any zeros, but if there's a reason it could be divided by 0, then you need to know what that point is. You also can't take even roots of negative numbers. Now ours happened to be an odd root, but if it had been even, the radicand of an even index can't be negative, so you have to watch for that. But we have found our critical value, and our critical value is 1. And so because our critical value is 1, draw a number line. And locate 1 on that number line. And then we need a test point on both sides. And a number that's to the left of 1 is 0. And a number that's to the right is 2. So those are our test points. And then we use our derivative. And we see that the cube root of 0 minus 1 is the cube root of negative 1, and 3 times negative 1 is negative and gives us the value negative 2/3. So our derivative is negative, which means our function is increasing. I'm sorry, not increasing. Misspoke. It is decreasing. And we see that down here on the graph. And then plugging in f prime of 2, we get a positive number over 3 times the cube root of 2 minus 1, which is the cube root of 1, and that's 1, so the answer here is just positive 2/3. But the key is that it's positive. Which tells us that our function is increasing, which we also see in the graph. And so we still follow the same testing procedure. Here again, find the intervals for which the following function increases and decreases. If you're going to graph the function, first of all, you would need to know where its asymptotes are. So, to begin with, we realize that f of x is undefined at x equals negative 1. So it would have an asymptote at negative 1. That's a vertical asymptote. To find the horizontal asymptote, you would take the limit as x approaches infinity or negative infinity, and you find that it has a horizontal asymptote at y equals 1. We also know that the x-intercept is where the value of y equals 0, which would be where x minus 1 over x plus 1 is equal to 0. And that would be where x minus 1 is equal to 0, or at x equals 1. So the x-intercept is 1, 0. And if you let x be 0 to find the y-intercept, you get -1 over 1, which is -1, and that gives you the point 0, -1. So we know a lot about the graph already. Now, if we find the derivative, since this is a quotient rule problem, the derivative is x plus 1 times the derivative of x minus 1 is 1 minus x minus 1 times the derivative of the denominator, which is also 1, over x plus 1 squared, and that turns out to be x plus 1 minus x plus 1 over x squared plus 1. And so f prime of x is equal to 2 over x squared minus 1. And that's never going to be equal to 0, so you're not going to get any critical values that way. And we've already determined that the function itself is undefined when x equals -1. The derivative is going to be undefined when x squared minus 1 is equal to 0, which would be when x squared is equal to 1, which means that x would be 1. So that gives us another critical value. And what we see is with the critical values at -1, that the value of the function is increasing, whereas the value of the derivative if we were to plug into, say, -1, I'm sorry, -2, because we're going to square that derivative on this side turns out to be positive. And then using the test point +1, f prime of x is equal to 2 over 1 plus 1 squared, which is still positive, which tells you then that your function is again increasing. And so this function is always increasing. But it's undefined at x equals -1. And notice that the reverse of this is not true because the derivative is always positive. For example, if we have f of x equals x cubed, f of x equals x cubed has the derivative f prime of x is equal to 3x squared. And because that derivative is equal to 0 only if x equals 0, notice that the derivative, other than that one point, the derivative is always positive. Because f prime of negative 1 would be 3 times negative 1 squared. And that's positive. And f prime of positive 1 is equal to 3 times positive 1 squared, which is also positive. And even though it appears that x equals 0 is a critical value, it actually isn't. It is a critical value only if it meets the criteria. It is possible for a function to be increasing on an interval even though the derivative is not positive at every point on that derivative. Now we'll learn why this is very important later, because x equals 0 is actually called an inflection point. It's only a candidate for the derivative. Now, you can use technology to find the derivative at a particular value, and there's nothing wrong with using that method rather than actually doing the arithmetic by hand. I have no issue with you doing that. Just show me how you did that. And it's also possible, as I showed you, having you graph this function. This is a good way to check your work. You can find out where a derivative is increasing and decreasing by finding the maximum and minimum of the function. But I want you to know how to use the derivative test. Because automatically knowing what the window is that you need to graph the function on to find the max and the min is not necessarily going to be the easiest thing. Why are we even studying all this? Well, we're studying this because it's good for something called profit analysis. So here we have an example of profit analysis. A company selling computers finds that the cost per computer decreases linearly. With the number that are sold monthly. And it decreases from $1,000 where you sell none to $800 when you sell 1,000. So the average cost function has a y-intercept of 0, 1,000, and it has a slope of negative 200 over 1,000, or negative 0.2, because, oops, forgot to put the pencil on, because the 2 points that you're given are 0, 1,000, and 800, I'm sorry, wrote that backwards. And when you sell 1,000 rather than 0, then you have $800 increase. And so that's what gives you the slope. because you have y values on top, and that means the rate of change is negative 0.2, as is stated here. And so therefore your cost function, your average cost function, is negative 0.2 times x plus, this is the y-intercept, so it's plus 1,000. And that's dollars per computer. And that means then that your cost function is only defined on the interval from 0 to 1,000. And this is for X computers. Sold monthly. So going on, okay, and I see my slide is a little messed up here, so let me fill in what you can't see. The revenue for X computers is equal to 0.0008 x to the third minus 2.4 x squared plus 2,400 x dollars revenue for X computers. And of course that is going to be the same as what our original domain was, which was with X going from 0 to 1,000. And that's sold monthly. We want to find the intervals when the profit is increasing. So in order to do that, we're going to need to find the profit function. And profit is going to be revenue minus cost. And so that's going to be 0.0008 x to the third minus 2.4 x squared plus 2,400 x minus the cost function, which was negative 0.2 x squared plus 1,000. And so your profit function is equal to 0.0008 x to the third, and since minus times that makes that plus and makes that minus, then negative 0.24 plus 0.2 is negative 2.2 x squared plus 2400x minus 1,000. And that's dollars profit for X computers sold monthly. Now, we could take the derivative and we could do the derivative test. But I'm going to let you here apply the numerical derivative. So keeping in mind, this is your profit function. I want you to actually enter your profit function the way that I'm going to show you on the next window. So now that we have the profit function, we need to find its derivative. So p prime of x is equal to 3 times 0.0008 is 0.0024 x squared minus 2 times 2.2 is 4.4 x plus 2400. And if you set that equal to 0, you need to use quadratic formula to solve it. And at this point, if you don't know the quadratic formula, you need to go look it up and use it. And it turns out that x is approximately $409.80. And so that is your critical value. Now what I want you to do is I want you to use your graphing calculator and I want you to enter the profit function by doing it this way. Y1 is your revenue function. Y2 is your cost function. Y3 is Y1 minus Y2, which is revenue minus cost, which is your profit function. And what we want to actually graph eventually is actually just your profit function. So you can actually turn this one and this one off, and then because they gave us a domain that x only goes from 0 to 1000, then we can use that to set up our window. And I actually did zoom 0 and then I came back and played around with these values a little bit to make it whole numbers. So I actually graphed this function to look at the profit function. So then once I graphed it on that window, this is what I saw that was actually confirmed. When no profits, I'm sorry, when no computers are sold, then obviously you're not going to make any profit. In fact, your profit may not even necessarily be zero, but the derivative, your derivative at x equals 0 of your profit function actually turns out to be positive, which means your profit is increasing. This was the 0 of your derivative. Which means your profit is at a maximum. That's going to be the main point of the next section, is this is how you find the maximum profit. And that if you make more than 409.8, in other words, here's a value that's more than that, you find that P prime of 1,000 is equal to a negative number. And it doesn't matter what those numbers are, it is simply that they are positive and negative. And that 409.8, in other words, 409 computers, produces your maximum profit. That's going to be the goal. So that's the goal of learning this entire chapter. And then to give you a graphical look at this, remember your cost is linear. So here your cost is constantly increasing. Your revenue is not linear. Your revenue is quadratic. But what you're really wanting to look at is your profit, which is the difference between your revenue and your cost. And so here's that critical value. And what that tells you is that when you make the 409th computer, your revenue is still increasing. Your cost is still increasing. But your profit at that point is decreasing. And at this point, your revenue is equal to your cost and your profit is 0. So as business majors, you should understand the importance of this diagram, this profit analysis diagram. So that's why graphing is so important, and why being able to take derivatives and use your cost functions and your revenue functions. So with this, we will end 13.1, and I will pick up with 13.2 and talk to you more about not just increasing and decreasing functions, but how that's important to finding your maximum profit and analyze how your business is doing. So with this, you can get started on the practice exercises for 13.1.